Let's talk about one more application of combinations. In fact, we're going to prove the binomial theorem using combinatorics. A binomial is an expression with two terms, like x plus y. If we take a binomial to an integer exponent, then expand and collect the like terms, what can we say about the coefficients of each of the terms? Let's look at an example. Let's look at x plus y cubed. X plus y cubed is x plus y times x plus y times x plus y. If we expand the x plus y times x plus y, we get x times x plus x times y plus y times x plus y times y. And then if we multiply and expand by x plus y again, we see x times x times x plus x times x times y, all of these 8 different combinations. And they appear by choosing x or y in the first factor, x or y in the second factor, and x or y in the third factor. When we multiply out these terms, we see some things that look like x cubed, some things that look like x times y, or an x squared y, some things that look like x times y, or an xy squared, and some things that look like y, or y cubed. When we combine, we see that there is one term that looks like x cubed, 3 terms that look like x squared y, 3 terms that look like x times y squared, and 1 term that looks like y cubed. Each of these terms looks like some number times x to the k times y to the n minus k. So what is this coefficient? What is the coefficient of x to the k, y to the n minus k in the expansion of x plus y to the n? Again, let's look at an example. Let's look at the coefficient of x squared y cubed in the expansion of x plus y to the 5th. Where do things come from that look like x squared y cubed? They have to have 2 x's and 3 y's that come out when you multiply x plus y 5 times. We might have a y from the first factor, a y from the second factor, an x from the third factor, an x from the fourth factor, and then to make sure that we have 2 x's and 3 y's, a y from the last factor. I would write that as y to mean that there were x's chosen from the third and the fourth factors, and then y's from the other 3 factors. I think you know the drill by now. We want to arrange all of the possible ways in which we can have 3 y's and 2 x's in an organized fashion so that we write down all of them and we don't miss any. And what we can see is that a term that contributes to x to the k, y to the n minus k corresponds to a choice of which k of the n factors contribute an x. The other n minus k factors contribute a y. And so the total number of terms that look like x to the k, y to the n minus k, which is the coefficient of x to the k times y to the n minus k, is n choose k. What we're saying is that if we expand x plus y to the 5th and then combine like terms, then we would expect that the coefficient of x squared y cubed is equal to 5 choose 2, which is equal to 10. We've just proven the binomial theorem that says when you want to expand x plus y to the nth power, the coefficients of x to the k times y to the n minus k are all of the form n choose k, and this is why the objects n choose k are called binomial coefficients. On the first page, we had that x plus y cubed was equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. What the binomial theorem says is that these coefficients are 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Let's take a closer look at these numbers. If you take these binomial coefficients and arrange them into a triangle, you start to see a number of patterns. So each row corresponds to different values of n. This is n equals 0, n equals 1, n equals 2, and the diagonals correspond to the same value of k. This is k equals 0, k equals 1, k equals 2, etc. When we calculate those numbers, we get this triangle. For example, we see 1, 3, 3, 1. Those are the coefficients in the expression x plus y to the third. These numbers 1, 5, 10, 10, 5, 1, those are the coefficients in the expression x plus y to the 5th. And we start to notice some patterns in this triangle. First, n choose 0, that's everything in this diagonal, that's equal to 1 for all n. And we should expect that because there's only one way to pick 0 elements out of n, and that's to pick 0 elements. Similarly, n choose n is equal to 1 for all n, because if you have n things, there's only one way to pick them all. You pick them all. Something a little bit less boring is that n choose 1 is equal to n. We see these numbers. 1 choose 1 is 1, 2 choose 1 is 2, 3 choose 1 is 3. And we should expect that because if we have n objects, in how many ways can you choose one of them? You can choose them in n ways. One more thing we can notice is that every number in this table can be calculated by adding the two numbers above it together. So 4 plus 6 is equal to 10, 1 plus 3 is equal to 4, and this lets us calculate subsequent rows of the triangle. So if we wanted to come up with what's the next row underneath 1, 5, 10, 10, 5, 1, we would add up 1 plus 5, we would get 6. 5 plus 10, we get 15. 10 plus 10, we get 20. 10 plus 5, we get 15. 5 plus 1, we get 6. And then the next row would be 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, 20 plus 15 is 35, 15 plus 6 is 21, 6 plus 1 is 7. And what this is telling us is that 7 choose 3, which is 7 factorial over 3 factorial times 4 factorial, gives us 35. There's a lot more interesting things happening in this triangle, which is called Pascal's triangle. Okay, see you next time.